Okay, so for section 1.2, we're going to talk about classification of differential equations. So, I mean, just like algebraic equations, how we have different algebraic equations like linear equations, quadratic equations, polynomial equations in general, to classify from cubic and on. I mean, even y equals 1, a number, it's a polynomial of degree 0, right? So, exponential logarithms, piecewise functions, anything. All right? Well, in order to classify a differential equation, number one, we're going to classify it by its type, by its order, and by its linearity. And then I'm going to give you a list of the methods of solution. Which ones are we going to cover? Because if you see the last page on the handout, it actually goes from A through Z methods of solution, and unfortunately, we don't have too much time to cover all of them. Okay, so number one, let's classify these equations by type. Okay, so by type, well, there's two types. Number one, ordinary differential equations. Let me do some highlights here. Okay, so we call them for short ODEs versus partial differential equations. We call them PDEs, right? For short. Well, what's the difference between the two? Well, for the ordinary derivative, the differential equations, those are written in terms of ordinary derivatives. That is, by the solutions to these equations are functions of one single variable, as opposed to partial differential equations, which are equations whose solutions are functions of more than one variable. So recall from calculus 3 that when we take the derivative of a function of multiple variables with respect to one variable at a time, that's essentially a partial derivative. Okay, so, well, examples of these equations. Don't worry about their solutions for now. Well, the first three equations are ordinary ODEs, because look at the derivative symbol. They have the actual d, as opposed to the remaining three equations. All right, these are the remaining three equations. Look at the derivative symbols; those are partial derivatives. So these are partial differential equations. All right, so these are PDEs. The first equation is known as the Laplace equation. Doesn't have anything to do with the Laplace transform, even though it's by the same mathematician. And actually, some partial differential equations can be solved using the Laplace transform, which we're going to do later in the semester. The second equation is the wave equation. It's the equation that is used to describe many phenomena related to waves, like the oscillations in the sea, like the tides, or in the world of music to describe the vibrations of a drum, or the vibrations of a guitar or a bass string. So these equations are used there. And the very last equation is the telegraph equation, which is an equation used in the world of telegraphs, right? So this is how we distinguish between an ordinary differential equation and a partial differential equation. Although we have to talk about notation, because there's different notations for ordinary derivatives, and there's also different notations for partial derivatives, okay? Well, and that's the next page, okay? So what we might want to consider here is, well, back when you first learned to differentiate functions, you were first introduced to the Leibniz notation, dy dx. And the reason why we learned that the notation first, it's because really dy dx, it's really the infinitesimal change of the dependent variable y with respect to the independent variable x. So you started with a delta y, delta x, which is really y2 minus y1 over x2 minus x1, which is the slope. The slope is the root of all evil for calculus and everything else, right? And then you wanted to find the slope. Okay, you use the slope to describe the steepness of a line, all right? That's number one. However, not all functions are linear, so we needed a more elaborate way to look at these slopes. for nonlinear function, and that's where the derivative came in, right? You know, the limit f of x plus h minus f of x over h as h approaches 0, you know, and that's the derivative. I mean, I don't want to go through the whole story from calculus. You already know all that, right? Then you learn another notation, the Lagrangian notation, and that's just using y prime, y double prime, y triple prime, depending on the order of the derivative. Okay, so that means we could rewrite the equations in the previous page. For instance, I'm just going to write the first two equations. Rather than having dy dx, I'm going to write, what was that? Y prime plus, what is that? 4y equals e to the negative 8x, right? I believe it was. Just make sure, yeah, negative 8y, not x. Okay? And the second equation can be written like, yes, it's the same one. So y double prime minus y prime plus 6y equals to 0. And that's actually a shorter notation because when it comes to working with some equations that will require a lot of work, a lot of steps, shorthand notation will come in handy actually, all right? Even though the dy dx is the most convenient way to express a differential equation because, for instance, like, okay, let me have enough space for this. D squared y equals to, over dx squared plus 16y, just to make up some differential equation. There's a point behind it. Okay, so for instance, this notation in a way is better because it's more descriptive, it's more explicit about which variable is the dependent variable and which variable is the independent variable. So when you have a quotient like this, describing a derivative, second derivative, nth derivative, the variable in the numerator, okay, is always the unknown function. All right, it's always the unknown function, or and the dependent variable. While the quantity in the denominator, or rather the letter or the variable you see in the denominator, represents the independent variable. All right, so that's our independent variable. All right, there's another notation you may see, especially in physics courses, when it comes to like problems related to like angular velocity, angular acceleration, rather. So there's this notation called the Newton's dot notation, like this one. X. Okay, let me change color. Okay, so x, instead of using the double prime or the dx dt, I'm going to go x with two dots at the top. These two dots means we are finding the second derivative of that variable x, which is the dependent variable, with respect to the independent variable. Well, it's not explicit what's the independent variable, but typically in this physics application, usually it's time, right? When we use this dot notation, that's for functions that depend on time, plus some 3x with a dot at the top plus another x equals to 0. Another example, for instance, well, this equation may represent some motion in the x direction because it's all x's. What about an equation that represents motion along the y-axis, vertical motion? All right. Or the very classical one. How about this one? S with double bar equals to negative 32. That's the acceleration due to gravity, right? In feet per second squared. It's integrate that twice to get back to the position. That's a very classical Calc 1 and Calc 3 problem, right? So, also, well, so I'm hoping all of you took Calculus 3 before. How many of you did not take Calc 3 before coming today to class? Okay, a few of you. Well, that's fine. No, you're not in danger. Anything we need from Calc 3 will be somewhat self-contained. All right. So, well, so and the reason to this is because when it comes to partial derivatives, this symbol, which is what we call Jacobi's D, it's what we call the Jacobian notation. Notice it's not the same straight D to denote the the ordinary derivatives. Well, there's also shorthand notation for these partial derivatives. So in this case, we use the subscript notation. U subscript x means we're differentiating with respect to x. U subscript y means we're differentiating the function with respect to y, having more variables, of course. But be careful, because when it comes to, twice with respect x, it's fine. No problem. I mean, however, when it comes to the subscript notation, here what do we have? U with respect y, then with respect x, we're going in this direction. On the Jacobian notation, that's the reverse. Here, it's the notation like this, okay? Because we're doing with respect y first and then with respect x. Otherwise, well, we're really finding the partial derivative with respect x to something we already differentiated with respect to y. That is, we do the inside part first and then the outside part. So there's an order of the operators here, right? That's what I'm trying to say here. Okay, so that means some of the partial derivatives we have in the previous page. Instead of having all these Jacobian symbols, which looks nicer, I like that symbol better. Looks great. But oftentimes we just want to go and write this quicker. So u twice with respect x plus u twice with respect y equals to 0. That's the first differential equation on the list at the bottom of the previous page. All right. And then what do we have for the second? Okay, I'm just going to give you the what's it called? PDE right here. Okay, so that is the other equation would be c squared times u would double with respect x plus u double with respect y plus u double with respect z equals what do we have on the right hand side? The time term in minus gamma. Okay, yeah. So that is the y term, u twice with respect to t, minus gamma, gamma u with respect to t. I always have a hard time writing this gamma symbol. Anyway. Okay, so that's a little bit on the types of differential equations. Ordinary and partial. This course, again, focuses primarily in solving ordinary differential equations, and still, we're gonna get to see every single method in the world. So just a few, and hopefully, again, we get the chance to get a glimpse of PDEs at the end of the semester. Okay. All right, now let's classify the equations by their order. Whether these equations are ordinary or partial, they may have an order. Okay, so the order of a differential equation, whether again it's an ODE or a PDE, it's going to be given by. Okay, let me highlight this. Is key. Is the order of the highest derivative in the equation. For instance, have a look at this funky equation right here. Okay, so in this case, which one do you think is the highest order for this equation? Any ideas?
d squared y over dr squared.
So that'll be the second derivative. Yes, okay. So be careful, guys, because let me highlight with the same color. Don't be fooled by these exponents. Again, dy dx to the third power is not equal to the third derivative. That's not equal. Well, actually, there might be a function that actually satisfies that condition, but not all functions satisfy. So that's why we can say, in general, that is true. Okay, so be careful. Yes, that's the first derivative. Whatever you get from differentiating one first time a function, and then cube that result. That doesn't mean the third derivative. So here. This is the highest order of the derivative. Well, actually, yeah, it's given away here, right? That's 2. Okay, and again, watch out with the exponent because that doesn't make the differential equation a third order differential equation, okay? So, I mean, I guess this is kind of straightforward. Look for the highest order derivative, ignore the exponents, if any. The trickiest part to classify differential equations, it's the next category, that is by linearity. All right. Okay, a bunch of symbols, a bunch of explanation here. Okay, what is this about? Okay, so this is what we call the nth order differential equation. That is, we have the n derivative and then one derivative less, and so on and so forth until we get to second derivative, first derivative, essentially zeroth derivative, which is just the actual function we're looking for. Okay? And that may be equal or not equal to something. Okay? By the way, if the equation is equal to 0, we say that the equation is homogeneous. Otherwise, if it's not equal to 0, we say the equation is non-homogeneous. We're going to get into that in detail when we get to these high-order differential equations. Okay. Notice something. Notice that the dependent variable, which in this case is y, which is what represents the solution to the equation, they are all raised to the first power. I know you're looking at 2n minus 1, but still, okay, this y right here, do you guys agree is raised to the first power, invisible one? Do you guys agree this is raised to the first power, invisible one? Same right here, invisible one. You know, this guy right here also invisible one. This guy right here also invisible one. Well, that's what makes a differential equation linear. All the terms having a letter y, well, not just a letter y. Whatever letter describes the dependent variable have to be raised to the first power. Otherwise, if you see another power like a 2, or maybe even an exponential function to the y, not to the x, that's no longer a linear differential equation. Okay, let's get into more details about this. Okay, so notice the coefficients are just constants. So the coefficients are either constants or depend at most on the independent variable, typically x. Of course, we may get to look at other differential equations where the dependent variable is x and the independent variable is t. You know, some motion, some horizontal motion, depending on time, for instance. All right. Well, what would make a nonlinear differential equations? Here's the two ways to determine that. Nonlinear functions of the dependent variable and or some of its derivatives appear in the equation. Or number 2, the derivative terms are either raised to a power other than 1 or multiplied by any of the functions in the previous point. Okay, well, so you can get a better overview of this linear, nonlinear. Actually, I have a bunch of equations right here that we are going to classify. Okay, let's do one at a time. So number 1, example number 1, give a complete classification of each differential equation. And we're going to be looking at crazy looking equations here. So number 1, equation in letter A. Any ideas? Ordinary or partial? Ordinary. We can see the straight D, not the curly D. Okay, ordinary. Great. Linear or non-linear? Okay, how do we know it's linear? Well, number 1, none of the derivative terms are raised to powers other than 1. Do you see those invisible ones? Okay. And number 2, do you see like that cosine having a y? No, it's a function of x. The coefficients, look at the coefficients. The coefficients are either functions of the independent variable, which is just x, or numerical coefficients like invisible 1 right here. So that makes it a linear. What's the order of the e? That's the highest order in the derivative, right? Letter B. What do you think? Partial or ordinary? Partial. So we can see the subscript notation for partial derivatives. Okay, linear or non-linear? This is linear because, okay, what's the dependent variable right here? The dependent variable is u. Notice those derivatives are raised to the first power each, right? Number 2, there's no product between any of these u's, or the other function right here is not a function of u. It's a function of one of the independent variables. So that makes it a linear. What's the order? Looks like it's order 2, right? So second partial with respect x, second partial with respect y. Well, that makes it second order. What about letter C? What do you think about letter C? Ordinary. What's ordinary or partial? Ordinary, okay? Whoops, ordinary. Okay, what about linear or non-linear? Oh, do you see why it's not non-linear anymore? Because look at some of the derivative terms are raised to the second power, to the third power. So it's like multiply. It's like having a y squared. What's y squared? Isn't that a parabola? That's not a line, right? Or even having plus y cubed, for instance. That's no longer a linear term. That's actually a cubic term. So that makes it non-linear. What's the order? 3. That's the highest derivative you see, right? I know it's kind of... Yes, do we look at this 3 or do we look at that 3? No, that's the exponent only, all right? That's exponent. So we're looking for this 3 right here to call it an order 3. Yes? Oh, 2 for the order in letter B? Oh, because, okay, how many derivatives did we take with respect x? 1 and then 2. And then how many derivatives with respect y? 1 and then 2, right? So we see two iterations. Okay, what about example letter D? All right, letter D. What do you got for letter D? Ordinary or partial? Ordinary, great. Linear or non-linear? Linear, okay. The derivative terms or the dependent variable is raised to the first power plus any other elementary function in there. It's a function of the independent variable, in this case, t, okay? That makes it linear. You'll see the difference. Like I say, the linear non-linear is a little bit tricky. That's why I brought a bunch of funky examples here so you can see the difference. Order, what's that? 2, good. Letter E, ordinary or partial? Ordinary, linear or non-linear?
Non-linear.
It's kind of similar to the previous example, but what makes it non-linear? Any ideas?
There's y's in the constant.
There's y's in the coefficients of the derivative terms, or there's powers of y's or their derivative, not the case. But actually, this guy right here, the e to the negative 2y, makes it a non-linear. What about the order?
5.
Highest order, that's 5. All right? Yes.
Does the 3 cosine y on the right side affect linearity?
Also affects linearity because that's an elementary function other than linear that has a y, in this case cosine. It's not a linear function. What about F?
Ordinary.
Ordinary, order, order 5, linear or non-linear? Actually very similar to the previous example, isn't it? Except it's all y's and x's as opposed to y's and t's. Right? Non-linear. Great. All right. What about the next one? Ordinary or partial? Partial. The subscript tells the subscript gives it away. Linear or non-linear? Non-linear. Okay. Yes. That's because we have the dependent variable either raised to a power or its derivative, that is in this case u, or that u appears as a cosine u or a sine u or a u squared, whatever. Okay. So nonlinear order 2 again, right? Okay, so the next example, letter H, is a little weird, I know, because we have more than one dependent variable. That doesn't make it a partial equation, no, because we're going to solve systems of, systems of differential equations in which just like a system of two equations with two unknowns, the solution is an order pair, that is two numbers. In this case, the solution to a linear system of differential equation will be two functions, an x function and a y function, both depending on one single variable. Well, of course, there are systems of partial, but we don't want to get into those. Okay, so number one, ordinary, linear or nonlinear. Okay, both derivative terms are raised to the first power, and also the functions as well. Order 1. In both cases, the highest derivative is the first derivative. Lastly, what do you think of the last one? Well, the curly D gives it away, right? Linear or non-linear? Non-linear, because we have these partial derivatives raised to powers, making them no longer linear. What's the order? Order 1, order 2, order 2, order 2. It doesn't matter if it's raised to the 2025. No, it's still order 2. Right? Order 2. And I believe we're done with the section pretty much, right? Okay, so the next page I would briefly like to discuss. At least this is the list of methods that I have found in many textbooks out there and also on YouTube channel. So, well, the methods we're going to do for this class are going to be the following. So that's actually next, separation of variables, linear first order. We're going to do some substitutions, which include homogeneous equations and Bernoulli's equations. Riccati's, Clairaut's, and Lagrange equations are also part of the general substitutions method, but unfortunately we don't have time to cover all of them. I wish I could cover them because especially Lagrange equation, it's an equation whose solution is given in terms of parametric equations, not just like a function y equals to x squared. I mean, you can always parameterize a function anyway, but the initial result, it's a set of parametric equations, which is a very cool method. So we're not going to look at those exact equations, and then we're going to look at higher order equations by, well, number one, reduction of order, higher order homogeneous equations with constant coefficients, and then non-homogeneous. We're just going to look at the superposition approach, the undetermined coefficient. There's another method called the annihilator method. It would take me at least 3 or 4 lectures to just describe what the method is, and in the end we would be equating coefficients like the undetermined coefficient, so I don't see the point of doing all that, right? So that's why we don't do that one. The operator method, oh yes, the operator method. So that's a very cool method to solve way higher order differential equations. Some equations are solved by simple integration, like first order differential equation. Integrate one time on both sides, that's your solution. We're going to use not a double integral, not a triple integral like in calculus 3, quintuple, octuple integrals to solve these differential equations. And although that sounds crazy, trust me, it's going to take a couple of minutes to evaluate one of those integrals rather than solving a bigger problem. All right, I'll show you when we get there, okay? What else do? We don't do the inverse operator. That's a lot of material. We're doing variation of parameters, okay? We're doing Cauchy-Euler's equation. Of course, we're going to look at solutions by series, but again, the remaining solutions by series, we don't have time. Frobenius method, that's the method I mentioned before, that one exercise takes about 9 or 10 pages to solve. Wait, I think I said 7 or 8, right? I already bumped the page. Anyway, you can make it 10 pages if you want. That's fine. So, Legendre, Hermits, Laguerre, those are methods you're going to learn in your higher levels of physics and engineering, mostly when you get to physics 3, when you get to what's it called, the quantum physics part, you may look at those equations. And hypergeometric, that's using in statistics, solving differential equations in statistics, and then the Laplace transform, which we're going to do a lot of it, okay? So again, you need a lot of that for signals, filters, beams in civil engineering, chemistry, biology, you name it, right? Okay, so looks like this is the end of the section, right?